Welcome to the ideal gas law. So we've covered several laws so far. So Charles Boyle and Gay-Lussac, we've covered those when we combine them into the combined gas law. So we saw an equation that looked like this. So it was like P1 V1 over T1 equals P2 V2 over T2. Okay, so if you'll take a look, if you were to mash the first three equations together and combine them, this is the combined gas law. So if you had a Charles law question, you could still use the combined gas law in order to solve the problem. Okay, so we've seen that in our previous lessons. Okay, and then last day we looked at Avogadro's law, the relationship between volume and the amount of the gas that was involved. So now what we're going to do is we're going to combine all of these into the ideal gas law. So there are some conditions that we have to follow. So this ideal gas, in quotation marks, it's supposed to be, hypothetical gas where there's no size to it. It always travels in a straight line because you've seen, in particle theory, they'll a little particle travel along, hit the wall, and then bounce off, and then go in a different direction and so forth. So we're gonna go with the assumption that okay, this gas is perfect. Okay, there's no size to it. It just travels in a straight line. It's not affected by intermolecular forces. So like if a particle goes by, another particle like this, they're not going to get attracted to each other using intermolecular forces. So basically, and if they do hit each other, normally if you hit the wall and so forth, you lose some energy and you kind of slow down and so forth. Okay, but we're going to assume that all the collisions that happen are perfectly elastic. So that means that there's no energy lost. So you're still going along at the same speed and so forth. Okay, so again, we talked about there's no attraction between and no repulsion and so forth between the particles. And because again, we're studying gases. I know we've looked at, once you drop the temperature far enough, it'll condense into a liquid form. But we're going to again assume that that's not going to happen either. So with all these conditions, there's this imaginary gas that we're going to study. So it's going to be like the standard condition that we're going to compare actual gases to. But so like this imaginary gas that we have, it works really well to kind of like, cause you can predict what gases will do using this model. So it's a close approximation of how the gases will actually behave. So even though we're making it, so that, there's no energy loss, there's no attraction and so forth. So when we have a model like this, we can use it to predict, again, like I was saying, predict what the real gases will actually do. Okay, so yeah, under ordinary conditions, most gases will obey these laws, and so they will resemble an ideal gas. Okay, so going with that now, we're taking all the different laws that we've again accumulated. Okay, so we have Boyle, Charles law and Gay-Lussac's law, which were part of the combined gas law. We learned about the Avogadro law last day. So now we're going to combine all of those, and they've formulated something called the ideal gas law. Okay, so here it is. Here's our new equation. Again, it's found on the back of your formula sheet as well, so it's something that you don't have to memorize, but you should know what the letters are. Okay, so P is still pressure. We're going to use that kilopascals unit. Volume is liters, so this is why I kept saying, try to just get comfortable with converting to these units because we will be using them later. So in this equation, you have to use kilopascals, liters here. Amount is still in moles, okay, but there's this new value. It's a gas constant, so they call it a constant because it's always the same number. Okay, it doesn't change, but again, with a lot of experiments and study, they figured out that we need this number here in order to analyze the behavior of gases, okay? So if you're interested, you can kind of look up how that was formulated. So anyway, we're going to use 8.3. I'm going to adjust it right now. I used to use 4, but the back of your formula sheet here has just 8.13, okay? So let's just change that, 8.13. Okay, when you go up to university and so forth, again, they'll expect more digits and so forth. But all right, so there's the gas constant, 8.13, 8.31, 8.31, sorry. And then the T is temperature, and again, look, it has to be in Kelvin. So make sure you make these adjustments as you're going through the problems today. That volumes in liters, temperatures in kelvins, pressures in kilopascals. And then if you look at the gas constant unit, it's quite complex, but it is just, yeah, kilopascals per liter per mole Kelvin. Okay, so just every time you write this constant, write all the units out and you'll have it memorized by the end of all your homework. Okay, all right. So again, now you've learned a lot of different formulas. When you did the combined gas law, remember there was always like you start with this and you do this to the gas, and then you have a final values, right? So you always have like a P, you give a 1, and then you have a 2 set of values, okay? So that's when you use combined gas law. But here, with these questions here, you're not going to have these two conditions. So that's how you differentiate the problems, okay? But again, we'll analyze that in a few days where we throw everything at you and then you have to decide what to use, okay? And then Avogadro's law, we did that the other day. Remember, the conditions are STP, okay? And you have to find the volume. You can use molar volume. So there's a few different conditions now you have to watch out for, but yeah, so just keep that in mind as we're going through today. All right, so again, the equations don't require two sets of conditions, okay? Hint, hint, hint. So just kind of keep that in the back of your mind as we're going through. All right, example 1. Okay, so we have a 5-liter tank of gas at a temperature of 25 degrees and a pressure of 200 kilopascals. So if the gas is oxygen, what is the mass of the gas? Okay, so let's write down all the information that we're given here. Okay, so we know it's oxygen. All right, so we have 5 liters of oxygen, or the tank is 5 liters. Okay, so I guess we could say is the volume of the tank is 5 liters. So the temperature is 25 degrees Celsius. Okay, I'm switching that to kelvins by adding 2.732. I'll just add it. 2.7315 kelvins. Makes it 298.15 kelvins. All right, and we have a pressure. It's in kilopascals. That's good. And we know that the gas is oxygen, and we need to find the mass of it. Okay, so again, we're going to have, we've had the scenario where it's like we have a gas, we do something to it, now we have these new conditions, right? That's combined gas law. Here we don't have two conditions, and we have to find the mass, okay? So we need to use the ideal gas law. Okay, so PV equals nRT. Okay, so there's the ideal gas law. So what you want to do here is you need to get the mass eventually. So in order to get to mass, we can go to get moles first, and then we need to go and find mass. Okay, so we're going to find mass using this formula here. So in order to get to the amount, though, using this formula here, we need to rearrange it. So I'm going to take both of these and move them. So we'll end up with PV over RT equals the amount, okay? So there's my formula. So I'm going to find the amount first, and then I'm going to find the mass using this here. So again, I need the molar mass of oxygen. So we have 2 times 16, which is 32 grams per mole. Okay, so let's go through the steps now. Okay, so here's my solving steps. So N equals PV RT, okay, PV over RT. So, and again, you can use the unit analysis method as well. That works. Or if you feel like you just want to start using the formulas, that's fine too. Okay, so we have 5 liters, all divided by 8.31, okay? Make sure it's 5.31 kilopascals liters. Okay. Okay, mole kelvins, like that. Okay, there it is. And then the temperature is 298. Okay, so let's crunch this out. Okay, so then we get, let's write it over here. Okay, so then we get the moles here. Okay, so again, carry a few extra digits. Again, just leave it in your calculator. And then from there, calculate the mass. So the mass is the amount times the molar mass. So, okay, etc. moles times 32 grams per mole. Okay, and this is the mass. So if we want to go through and look at the sig figs here, we have 3 here, we have 2 there, we have 3 there, so 2, 12.9 grams, okay, and therefore the mass of oxygen is 12.9 grams. Okay, so there, you've used your first ideal gas law. You've been, just go through, make sure you're calculating things in the right spot, and then I'll get to your final answer there. Okay, so what you're going to do here, if you look at your little guide here of how to go about calculating all the things here, we always start with volume and then we kind of head towards moles and mass, okay? So volume and then we head towards things. So the way you're going to set up your unit analysis step, just because there's so many things here that are giving you like, what do I write first? So what you're going to do is write volume, and then from there you're going to go through and slash out, get rid of units that you don't need, okay? So this is our action and our solve step at the same time. All right, so our goal here is to find the mass of oxygen here, okay? So we're going to start with the volume that we're given here. Okay, so 5 liters. So we want to get rid of the liters, okay, first. So what you're going to do is if you look at, all the different values that you are given, you have this gas constant that can help slash out the liters that you need, okay? So if you take a look, it's 8.31 kilopascals liter mole per Kelvin, okay? Or mole Kelvin. So right now liters is at the top. So we don't want liters to be at the top. So we don't want this number right beside 5. We want to flip it. So we're going to have our gas constant flip here. And we're going to go kilopascals liters like that. And then the mole Kelvins goes to the top. Okay, so that's why make sure get these units memorized so that you know, or you don't even have to memorize it. They're on the back, okay? All right, so you're going to slash the liters. Okay, so now we want to get rid of, everything and then get to mass, okay? So, so the next thing here, of all the values that we have here, let's put temperature in somewhere, okay? So temperature, see it's kelvins. We already have kelvins at the top, so I know kelvins has to go to the bottom here. So temperature goes to the bottom and we have to divide it away, okay? So there goes kelvins. All right, so there's kilopascals. So let's put the pressure in. So again, I know I have to put kilopascals at the top here so that they cancel out. Okay, so that'll be over 1. So there goes kilopascals. Okay, so what am I at now? I'm at moles. So how do I get rid of moles? Well, that's the molar mass step now. Okay, so again, if you're following the formula sheet that you guys have here, so we're trying to go from volume to moles, And then when we go to moles, we need to use molar mass. So again, we're still using kind of this flow chart like guide so that you can get through to your calculations. Okay, so now we need to use molar mass. So again, we're not going to flip it because moles is already at the bottom. So 1 mole goes there, and the 32 grams goes to the top here. Okay, so that will cancel out our moles, and we'll get to the unit of mass, which is what we wanted. Okay, so if we take that, so now we got 5 liters times 200 times 32 at the top divided by 8.31, okay, equals 12.9. 9155, etc. Okay, so that's the mass. And we need 3 digits, 2 digits, so we just need, 3 digits here. So we need 2 digits, so 13 grams. Okay, like that. All right, so and then we already have our therefore statement from above. So that's how we use the unit analysis method. Start with volume. Start with volume, and then you, I would throw in the R value next, figure out which way that flips, and then you can throw the other ones in to cancel out the units. And then molar mass is that last step here. The molar mass is that last step. So once you get through here and hack through the ideal gas law components, then we get to the molar mass. Okay, and there it is to get rid of all the units that we don't need, and then we end up with 13 grams at the end. Okay, so and that's what we had here as well. I guess I should have had 13 here as well. Anyway, okay, so I'll change that in a sec. Okay, so we have to find the volume of 100 grams of oxygen gas at STP. So right away, STP, you see that condition, so start thinking molar volume, okay? So we know the mass of oxygen is 100 grams. All right, so we have to find the volume of oxygen. Okay, but we know the conditions as standard temperature and pressure. So we can use molar volume in order to get there, okay? But remember, molar volume means that we would jump between the amount and volume, right? So but right now we're mass, so we need to go from mass to moles to volume. So in order to do that, for the formula people, you need to use this formula. So mass over molar mass, and then when you get to here, remember you have to either multiply by 22.4 liters per 1 mole, or you have to multiply by 1 mole divided by 22.4 liters. So hopefully you did enough practice questions that you realize, oh, when I need to find volume, I use this one, okay? The liters is at the top. When I need to find amount, I use this one here. So in this case here, we're using this one today. So we need to multiply by 22.4 liters per 1 mole. Okay, so let's put our plan into action here. So we'll find the moles of O2. So we're going to do the formula method first. So we have 100 grams, and we're going to divide by the molar mass of oxygen, which we'll find right now. So we know that oxygen is 16, so 2 of them together will make a 32 gram per mole molar mass. Okay, all right, so we're going to divide that molar mass. And we will get 3.125 moles. Okay, I'm going to carry some extra digits here because I'm not finished my question yet. Okay, so from there, now that we found the amount, we need to find the volume. Okay, so the volume is found by multiplying by the molar volume value there. Okay, so we're going to take our amount and we're going to multiply by the 22.4 liters per 1 mole. Okay, so when we do that, we get 70 liters, like that. Okay, and I'm looking for my sig figs here, so I have the only number that I was given here was the 100 grams, and there's 4 digits to it, so I'm going to change this so that I have 4 digits. Okay, so Okay, so it'll be 70.00 liters to have 4 sig figs. So final statement here. Therefore, the volume of oxygen is 70 liters. Okay. All right, so here's how to do it if you want to use the unit analysis method. Okay, so your given and required steps are still the same. So make sure, get these all written out. But your plan and your solving step are all one, okay? So your goal here is to get the volume of oxygen. So you need to, okay, what you're going to do is you start with your mass, which is 100 grams, okay, of oxygen, and then you're going to take your molar mass and, to stack it this way so that the grams will cancel out, okay? And then once you get to the amount, you need to go to the volume using your new conversion here. So again, if you're stacking the 22.4 liters, right, is equal to 1 mole, right? So when you're stacking this, you want volume, so you want liters to be at the top, okay, because then the moles will cancel out at the bottom here. Okay, so there goes the moles, there goes the grams, leaving you liters, which is what you want. Okay, and if you go through and calculate this out, you will end up with 70 as well, and then with your sig figs, 70.00 liters. Okay, all right, so I know with the one up here, it's a little tricky to do unit analysis, so I recommend like just using the formula here for this one. If one of you can kind of formulate something and then present it, I'll give you a pile of chocolate bars, okay? So yeah, you can send that in to me. But for now, yeah, just when it's ideal gas law, just kind of use the formula. When it's the other stuff, yes, you should be able to make a plan here and then use unit analysis method. Okay, I want to look at example 2 again from a different perspective. We used molar volume in order to calculate out the idea of, molar volume to calculate out the volume of oxygen here because we knew the conditions were standard temperature and pressure. So if you look at your formula sheet here on the back, so you'll see that, you bounce between these islands and so forth. So if you have an amount, if you have mass, you go to moles first. But once you have moles, in order to get to volume, again, you can use the molar volume that we looked at. And again, this is for the conditions of standard temperature and pressure, which is 0 degrees Celsius and 101.3 kilopascals, okay? But I want you to understand that the ideal gas law that we're looking at today, it is for any gas, for any temperature and any pressure. So for this one here, it's supposed to be for standard temperature and pressure, okay? But for any other gas, we would use this one. But if you wanted to use the ideal gas law for a gas that's at standard temperature and pressure, it would still work. So I'm just going to show you that right now, that if you ended up calculating it using this method, it would be fine as well. I would recommend doing this one because it's a little less calculations and numbers to juggle with, but if you ended up using this one, it would be okay. All right, so here, let's take a look. So here's example 2 again. So we're going through and finding all the information that's given. So we have our mass. Okay, so we have our mass of 100 grams, and then we have standard temperature and pressure. So the temperature is 0 degrees Celsius. Okay, that's the standard temperature. So if you add 273 to it, you would have this in kelvins, okay? And then the pressure is in kilopascals, 101.3 kilopascals. And again, that's on the formula sheet as well. So we know we know the mass, we know the temperature, we know the pressure. Our goal is to find the volume of oxygen here. Okay, so given that we have mass and we're dealing with moles and so forth, we're going to use the ideal gas law. okay? PV equals nRT. So again, what we're going to do is we need to go from mass to volume somehow, okay? So we need to go to the moles island first. So mass to moles to the volume, okay? So in order to go from here to here, we're going to use this formula here, okay? And then we're going to use the ideal gas law, okay, to get to here instead of using the molar volume that we did last time. Okay, so we need to go from mass to moles. We're going to use this formula here, and then we're going to use the ideal gas law second. Okay, so for the ideal gas law, we need to get to volume. So what we're going to do is rearrange this so that volume's by itself. So we're going to throw the P over. So since it's multiplied on this side, we're going to divide it away. There it is. Okay, so now we have our second equation here that we're going to use. Okay. So we're going to find our amount first. We're going to do this by dividing by the molar mass of oxygen. Okay, so 2 times 16 is 32 grams per mole. Okay, so there's the molar mass. So we're going to take that and divide it from the mass. Okay, and then we get 3.125. All right, so, and then from there, so this step's still the same as before, right? But from there, we're going to use the ideal gas law formula. So we're going to go through here and fill everything in here. So we now know the amount is 3.125 moles. Okay, here's our ideal gas, or gas constant here. So remember 8.31 kilopascals times liters, all divided by mole kelvins. Okay, and then temperature. So we've already converted it to kelvins. There it is. And then we're going to divide all of it by pressure. All right, so when we do that, I'm going to multiply all those top values together, and I'm going to divide by the pressure. Okay, so then when we do that, we will end up with 70.02, etc. Liters here, okay, when everything cancels out here. So again, if you wanted to kind of be the unit analysis person and cancel out the units, you can. So see how moles, moles, kelvins, kelvins cancels out, and then kilopascals underneath cancels out, so that we have liters left, okay? So yeah, so then if you look up here, you know, it was, you know, like exactly 70, I guess, when we calculated here, but here, same thing with the units. It's 70.02, so it's close, okay? So either way is fine, okay? But you'll find that when you use the molar volume here, it's a lot less work, okay? Because here you're going to be, you know, using the gas constant and converting the temperature over, and then using the pressure. So you're juggling a lot more numbers. So if you know you're at STP, then just use molar volume, okay? All right, and then P is what we found before. So therefore, the mass of the volume of oxygen is 70.02 liters. Okay, so I'll accept both methods are answers. I realize they'll be slightly different, but it's still close. Okay. Okay, so when I make a video, I make bits and pieces of it, and then I realize I made a mistake or forgot something, so I go back and make another video and throw it in somewhere. So anyway, I went through the video and just did the formula method, and I made a comment like, don't worry about the unit analysis method today. I'm going to show you how to do that. I'm just going to do it at the end of the video. So if you want to just skip through to the end of the video to see the unit analysis method, then do that, okay? a lot of the homework question solutions will have it in the formula method. So if you wanted to just kind of see what was going on there, you can, also check out that part of the video, okay? Okay, and also I made a really big sign so that you should be able to find this, like if you skip through the video. So if you can find this, stop there and then go back and, yeah, just start the video from there. Okay, but if you are a formula person, just keep watching the video in this order, okay? And then when you get to the big unit analysis sign like this, just stop. You don't have to watch the rest of the video. Okay, so here's example 3. So we're going through, we have to find the temperature of 2.5 moles of a gas that occupies a volume of 56.5 liters at a pressure of 121.59. Okay, so let's write that all down. So we know the amount. Okay, so hopefully you're at the point where you can recognize it from the unit what it is. Okay, so that's N. This one's liter, so that's volume. This one's kilopascal, so that's pressure. Okay, and then write them all down. Okay, so when you do that, we have all the given information and we need to find the temperature. Okay, so yeah, we have volume, pressure, we have the amount. So right away, if you're trying to select what method to use, because you have moles here, but we're not at SDP, we know we have to use the ideal gas law. Okay, and that is PV equals nRT. All right, so from there, let's rearrange it. So we need to find temperature. So we're going to boot these two over. So right now they're multiplied. So I'm going to divide it away on the other side. Okay. All right, and we're just going to double check everything's in the right units. Yep. Okay, so so to get temperature, we need this formula here. So we're going to look at what values do we need in order to calculate it. Well, we need R. So R, again, we have as 8.31 kilopascals, liters over mole kelvins. Okay, so there's our gas constant. Yeah, and then we already have our amount in moles, and we have our pressure. Okay, so we don't have to make any conversions or extra steps here. We just have to plug it all in. Okay, let's do that now. I'm going to do it right here. Or no. Okay, it's fine. All right, so pressure is 121.59 kilopascals. The volume is 56.5 liters. Okay, it's all over the amount, which is 2.5 moles, and the gas constant here. Okay, so 8.31 kilopascals liters over mole kelvins. Okay, so again, if you want to slash out units, you can. So see how mole, and then this is underneath, so those will cancel out. And now you can look at it as these being the top and the bottom. So this one will cancel out this one will cancel out this one. And then what are we left with? Well, we have, so again, if you're using an analysis, it's like 1 over K. So that's what's left. But if you clean it up, that's like 1 divided by 1 over K. So we don't multiply fractions, we multiply by the reciprocal. So we flip the K up, and then we end up with K. Okay, so anyway, if you wanted to use the unit analysis here, but it's a little bit tricky with ideal gas law. So that's why I just kind of use the formula, and then no temperature, well, you have to have the units kelvins, okay? All right, so 121, we're just multiplying out now, times 56.5 divided by, okay, so 2.5 and 8.31 at the bottom. So you should end up with, okay, a number like that, kelvins, and then we're checking our sig figs here. So I threw 3 there, 3 here, and 5 there. So 3, okay, 331 kelvins here. Okay, so the temperature of the gas that we don't know what it is, so therefore temperature of the gas is 331 kelvins. All right, a couple more examples, I believe. Okay, just want you to get good at these. Again, I'd say the toughest part here is just kind of learning to rearrange the equation, just making sure you're double checking your work, putting in the values in the right spot. I guess the ones that are trickier is when you have to go multiple steps and so forth, but otherwise, yeah, it's should be straightforward today. Okay, all right, so we have a blimp here, has some gas in it. Okay, so the volume, so we'll just write down all the stuff we know here. So we know the volume is 2.5 times 10 to the 7 liters, okay? So big number here. And it usually operates with a gas that has a temperature of 12 degrees Celsius and a pressure of 112 kilopascals. Okay, we want to know what amount of helium does the blimp contain. Okay, so then we want to know N, so helium. All right, so what, and also after that we need to find the mass of helium. So we want to know what amount of helium, how many particles, and or how many moles of the helium, and then the mass. Okay. All right. So here's our plan here. Okay. So we don't have STP conditions. We don't have like a first condition and a second condition. So we know we have to use ideal gas law. Okay. So PV equals nRT. Just throw it down, and then so then from there we want to go to moles eventually. So and then to the mass island. So we need to go from moles to the mass island, okay? All right, so how do we get to moles? Well, we know, you know, all this information here. We also know the gas constant. Okay, so we can use the ideal gas law in order to find the moles, okay? And then from there, we'll go to the mass island. So, so yeah, right now, we just have to get to the moles island using ideal gas law with all this information here, okay? All right, so ideal gas law first. Okay, and then we'll use our molar mass to get to the mass island. Okay, but you guys know it as this formula for the formula people. Okay, so ideal gas law, we need to get to moles, so we're going to rearrange this so that we get to moles. Okay, so N equals PV over RT. Okay, that's step one. And then step two, we're going to go get mass by taking the amount and multiplying by the molar mass. Okay, so molar mass of helium. Okay, so let's write that here. So the molar mass of helium. So remember, any of the noble gases are not diatomic. Just write helium. Neon, argon. Okay. All right, and the molar mass is 4 grams per mole. Okay, so you're just reading it right off the periodic table. Okay, so yeah, let's put our plan into action now. Solving step here. Okay, given, required, action, analyze, and solve. That's what GRAPH stands for. And P will be present, like make a therefore statement. Okay, all right, S is, okay, so we have our ideal gas law equation. Okay, so we're assuming that this gas has ideal gas law properties in order to predict or calculate some information out here. All right, so we have pressure. Okay, we have volume. Making sure everything's in the right units, good. And the constant. Okay, so hopefully now that we've completed several of these examples, you have the units memorized here. Okay, but again, when in doubt, it is on the back of the formula sheet. Okay, and then temperature. Oh, we're not in kelvins yet, so let's add our conversion here. Okay, so we'll get to 285.15. All right, and then if you are a unit analysis person, you want to make sure everything's in the right spot. Okay, kilopascal, kilopascal, liter, liter. Okay, those are gone. All right, so then from here, Kelvin, Kelvin, and this is that case where it goes 1 over 1 mole. So when it flips up, it'll just be moles, okay? All right, which is what we want. So let's go through, calculate these out. Okay, and we end up with just writing them all out on my calculator here. All right, moles. Okay, so we got a big blimp here. So yes, we're gonna have several moles of gas in that blimp. Okay, so let's look for our sig figs here. So we have 2 digits, okay, 2 digits, 3 digits. So we need an answer with 2 significant digits. So I'm just going to go 1.2 because I'm going to just keep these 2, but the 8's going to round up this 1 times 10 to the 2, 4, 6 spots. Okay, moles. Okay, so that's what we have here. Oh, actually, you know what? We are not done. We need to go to mass first, okay? And then I'll round this up after, okay? So the mass of helium, so let's get to there. Okay, so the mass is the amount times the molar mass. Okay, so I'm not going to write this again, or I will write this again. 35 moles times the molar mass, which is 4 grams. So hopefully you still have this in your calculator. Times 4. Okay, now we get to our big mass here. So 4,726. Okay, writing them all out as well, and this one's grams, okay? Because again, you see the moles and the moles will cancel out here. Okay, so now that we have to present our final answers here, I want to write it in scientific notation. So 1.2 times 10 to the 246 spots, moles. And then this one here is, again, you need 2 digits, right? So you need the 4.7 at the front here. The 2 won't round up to 7, and then you're going to move the decimal. 2, 4, 6 spots. Okay, grams like that. 2, 4, 6. 2, 4, 6. Okay, so there's your mass, and there's your amount. So make a final statement here. Okay, so you wanted to know what amount of helium it has and what mass of helium it has. Okay, so again, make sure you're using the keywords. A lot of you are still going, the blimp had 1.26 moles, and it's like, I want to know if you understand what it is that you just found here, okay? Do you know how to use your proper communication skills using the proper terminology? Okay, so the amount of helium in the blimp is 1.2 times 10 to the 6 moles, and the mass of helium is 4.7 times 10 to the 6 grams. Okay, so make sure your units are there. Try your best to get to the right sig figs, and then make sure, use the keywords. The amount is in moles, mass is in grams here. Okay. Okay, we're going to do one more just to make sure it's good, and then I want you to go practice a bunch and just be careful. Please check your work and then try the checkpoint, okay? All right, so as usual, I've seen a lot of you now writing, graphs like along here, writing out the information that you know, so that's really good, okay? It's a good technique to pick up so that you can kind of apply it to a lot of the sciences. All right, so calculate the volume of nitrogen gas. So we know we have a mass, right? Again, you should be able to recognize grams. Okay, that's mass of nitrogen gas. So nitrogen is a diatomic, N2, 32.4 grams. Okay, so we know the mass in a container at a temperature of 25 degrees Celsius, and we know the pressure is 96.4 kilopascals. Okay, all right, and so our goal here is to find the volume of nitrogen. Okay, so I'm noticing here we're not in kelvins, so I'm going to switch that over. So we're going to add 273 to it, and then we get 298.15 kelvins. Kilopascals, good. Okay, we have our mass. All right, so again, if you're trying to determine what plan of action to implement here, you are looking at, you have mass. As soon as you have mass or moles, you know you don't use the combined gas law because the combined gas law doesn't help you find those, okay? And then molar volume, we don't use that because our conditions aren't STP, so we have just ideal gas law left. Okay, so today you're just practicing ideal gas law. There will be another day where we're going to mix everything up, okay? All right, so write the formula out, PV equals nRT, and then, okay, you decide, all right, I got to find V, so I'm going to kick the P over that way, and so again, you should be good at rearranging these equations, regardless of what they are, okay? So kick that over, so since it's multiplied right now, we're going to divide it away, okay? All right, so we have our volume now, we have our, we have all this other information, we know our R. We know our R is the constant, okay, 8.31, and what was it, kilopascals, liters, mole, kelvins. All right, and then we know our temperature, we've converted to kelvins, we don't know the amount, okay, so we need to find that. So we're gonna go from mass, okay, to moles. And then we'll go to volume, okay? So what we're gonna do here, again, we need to use molar mass here, and then we need to use ideal gas law here, okay? So this is for the formula people, okay? And I guess unit analysis people as well. We're gonna use that formula at the end, but to get from here to here, we're gonna use this formula here where we're gonna divide by the molar mass. So we need to figure out the molar mass before we keep going here. So the molar mass of nitrogen is 2 times 14.01. So that will be 2802. Okay, yep, and grams per moles. Okay, so we have our molar mass. Okay, so we have everything, all our given information, so we can get rolling with this problem. So again, we're going to do this first, and then that second, okay? So again, yeah, so there we go. So the amount. Okay, so we have, so this is for the formula people. Okay, we have the amount is found by taking the mass, which we have at the beginning, 32.4 grams. We're going to divide by the molar mass, which is, 28.02 grams per mole. Okay, and then we end up with an amount of this, Okay, but we're going to carry these digits in our calculator. We're not going to clear it. And now we're going to go to the ideal gas law. Okay, so again, if you are the unit analysis person, just, to just line it up like this. Okay, like that, and then you get this answer as well, okay? All right, so now we know our amount, so you're just gonna use it, carry all the digits in your calculator, and then multiply it by this number, gas constant. Okay, so remember that K is lowercase, so just go dot liters, mole, dot kelvins, like that, and then we're gonna multiply by the temperature, which was 298. Okay, and then divide all of this by the pressure, which was 96.4. Okay, kilopascals. All right, so we're going to go through, calculate that out. So again, yeah, just, double check your units here. Kelvin, Kelvin's going. Kilopascal, kilopascal will go, so that leaves liters. Okay, so we're going to multiply the amount by the gas constant times the temperature. and then we're going to divide by 96.4. Okay, so now we have a volume for nitrogen, 29.719, okay, and checking my sig figs here, I see 3 here with the mass, and I see 2 with the temperature and 3 with the pressure, okay, so we need 2. Okay, so we're just going to change this to 30 kelvins. Oh, sorry, liters. Okay, so now we have everything, so we can make our therefore statement. Okay, so calculate the volume of the nitrogen. Therefore, the volume, there's our keyword, of nitrogen is 30 liters. Okay, all right, so hopefully that wasn't too bad today. Just really, lots of values to crunch out with this ideal gas law, but if you keep your work organized and list off all your givens and your unknowns, and then set your plan out so you can kind of follow a little guideline of what you should do first, what you do next. This is like the most challenging question you'll see, where you have to do a couple steps, use a couple formulas to get to your answer. Okay, so just practice these so you know what to do, and then always be paying attention to what I was teaching you today, where it's like, okay, if you have mass or moles, you're not going to use the combined gas law. And then if you have STP, then use molar volume, but otherwise it's ideal gas law. Okay. All right. So yes, just again, practice a few more. I know there are lots of examples here, and then try the checkpoint. Okay, so we're doing example 2 again. We saw the first time it was just using molar volume. The next time we use the ideal gas law, but we use the formula method. So now we're going to use the ideal gas law, but we're going to use the unit analysis method here. Okay, so our A and F step kind of are combined. We just kind of do them together. So we know we need to find the volume of our gas. And so in order to get our volume, what we're going to do here, so here's our ideal gas volume, we need to go through these steps here. So we have mass, so we're going to use molar mass to get to moles, and then from moles we're going to use the various parts of the ideal gas, like pressure, volume, right, without using the formula, in order to get to volume. Okay, so it's all about kind of canceling out those units. Okay, so we have our R value here as well, so now we're going to start with mass. Okay, so there is the mass. And then, so remember, from mass to moles, we need to use the molar mass. So we're going to flip it. Okay, and write the mass grams underneath. Okay, so that takes out our first unit there. All right, the next step is to, we need to get rid of moles. So we're going to use our R value now and stack this in a way so that moles will cancel out. So see how moles is already at the top? We have moles at the bottom here. So we're going to leave the R value upright. There is an upright position. Okay, so there we go. So the moles will go to the bottom, kelvins will go to the bottom, liters and kilopascals will be at the top. So we have taken care of our moles. Okay, so our goal here, remember, is volume. So we need liters to be left over. So we need to take out kilopascals and kelvins. So we have our, I don't know, doesn't matter which one you want to get rid of first. So let's say kilopascals. So we have pressure here. We have to put it underneath here that way. Okay, so there goes the kilopascals. Cancel, cancel. All right, kelvins, there it is. I'm going to put that at the top. So you can put 1 over, or I'm just going to stack it up here because there is a spot. Save space. All right, so kelvins are gone. So that leaves me liters, and that once I cancel out all the other units, I know I've picked all the numbers that I've added in all the numbers that I needed to put into this equation, to this calculation, so I can get to the answer here. Okay, so 100 times 8.31 times 273.15 divided by 32 times 101.3 at the bottom, and we get to 70.02 liters, which is what we had from the previous question. Okay. All right, so there is the unit analysis of example 2. Okay, so the nice thing is, look, a lot less work than what you saw there with the formula method. Okay. All right, here's example 3. So I've gone through, grabbed it from the previous question I did. So we have a temperature, we have to find the temperature, and we have the amount in moles. It has a volume of 56.5 liters and a pressure of this here, okay? And we know the R value, that's a constant. So our analyze and solve step will happen at once here. Okay, so our goal is to get to temperature. So where are we right now? We have our amount, and we need to go get the temperature along this line here, okay? So normally I would say, start with mass if you have mass, okay? But we don't have mass. We're just starting here at moles. So from here, we just need to figure out how we need to stack everything up. So I would start with the R value first. I would change the R value so I have the units in the right place. So the units for temperature are kelvins. So right now the R value here, the kelvins are at the bottom. So I'm going to start with, in order to find temperature, I'm going to flip the R value. So we'll put 1 mole kelvins at the top, and then we'll put the 8.31 kilopascals per liter times liter at the bottom, okay? So now we have the units the right way, okay? So again, if we have mass and so forth, start with mass, but when we have moles to start with, what I want you to do is just take the R value, write that the right way. So again, we're trying to get K by itself, and then from here, we're gonna hack everything away. Okay, so we could start off with, say, getting rid of the moles. So in order to get rid of moles, we'll put 2.5 moles down here. Okay, so they'll cancel out. Whoops. So they'll cancel out the moles here, okay, but not the 2.50 part. Okay, and then from there, so I can kind of do this in pieces if you want. So the moles is gone. The kelvins, where will those go? Oh, no, we want to keep those. The kilopascals, we want to get rid of those, so we're going to stack the pressure up here. Okay, so there it is. Kilopascals. So we want to get rid of liters as well. So same thing. We want to stack up the volume up here as well. Okay, and there it is. Liters is gone, liters is gone. All right, so now we're checking everything. Moles is gone, kilopascals gone, liters are gone, and we have kelvins up in the air. That's where we want it to be. Okay, all right, so if we calculate this out now, okay, we'll end up with 330. So we have 3 digits, so 331 kelvins, like that. Okay, all right, and I won't do the therefore statement. Or I will. Sorry, never mind. Okay, so therefore the temperature, okay, of the gas is 331 kelvins, like that. Okay, so again, up here we had our mass, so we started with mass and hacked it apart. Here we started at moles, so from here when we have this, go from moles to where we need to go, use the R value first and then manipulate that so it gets to the right unit, okay? And then you know how to stack up the rest of the things. Okay, all right, example 4. So, okay, we have a blimp here, we know the volume, okay? It usually operates with a gas with a temperature of 12 degrees, which is converted to kelvins, and a pressure of 112 kilopascals. Okay, we know the R value. What amount and what mass of helium do we have? Okay, all right, so here's our plan. We have a lot of information here, but we need to get to amount and then mass. So we are going from here to here to here, okay? So if we have volume, we start at volume. Yes, we have the volume. So we're gonna go from volume, and then using all the pieces of the ideal gas law, okay, get to amount, and then using molar mass, we'll get to mass. All right, so let's start with volume here. Oops, and then this is our analyze and solve step all in one. Okay, so we are going to find both of these. So I will go through, yeah, we'll just go find mass, okay? So mass of helium. So what you're going to do here is you're going to go volume, start with that. All right, and then I'm going to use the R value next. So see our liters is already at the top of R, so we're going to flip the R. So the mole in kelvins comes up, and the kilopascals and liters goes to the bottom, so the liters can cancel out. Okay, so from there, we use the R value to figure out where to put everything else, okay? So we're trying to find moles first, so we're gonna, and then also find mass at the same time, okay? All right, so let's get rid of the, I don't know, the kelvins next. So that's the temperature, so I'm just gonna go 1 over 285.15 kelvins here. All right, and then so those are gone. Okay, I'm going to get rid of the pressure as well now. So that's a kilopascals at the bottom, so I'm going to put 112 at the top here. All right, so those are gone. Okay, and now I just have moles. So what I'm going to do is I'm going to calculate this out right now in order to find moles. So, and then I'm going to do the next step. I'm going to add the molar mass in here to get to the mass eventually. Okay, so right now let's just kind of stop and look at the amount of helium here from just this calculation here. Okay, all right, so 2.5 to the 7 times 112 divided by all that stuff at the bottom. Okay, ends up with this many moles, okay? All right, but that's, we're gonna keep going here with the mass unit analysis calculation here. So that part there is just the moles, okay? But we want to get to mass in grams, so we're gonna use our molar mass of helium, okay? So again, we have moles right now, I want grams, so I'm going to just stack this way. And there we go, moles is at the bottom, so I can now cancel out the moles to get to the mass. So I'm going to multiply my previous answer by 4, and then I will get the mass of helium to be this. Like that. Okay? All right, and then from there, we want to report those. How many digits here? We have 2 here, 3, 2. Okay, so 2 digits here. So we need to get to scientific notation here. So 1.2 times 10 to the 246 moles. So again, if you're looking here, I want to keep that 1. This 8 rounds up, makes a 1 a 2. So 1.2, and then I move the decimal to here, right? So that's 1.2, and this is 4.7 times 10 to the 6 grams. 2, 4, 6. Okay, this 2 won't round up to 7. All right, and there are your 2 answers here. Okay, so therefore, the mass, or I guess I'll say the amount first. The amount of helium. Okay, so that's key. Use the keyword. Okay, the amount of helium is 1.2 times 10 to the 6, and the mass of helium is 4.7 times 10 to the 6 grams. Okay, and again, if you wrote these, I will accept them, but try to practice your scientific notation too. Okay, so here's the last one using the unit analysis method. So again, yeah, so I went through and found all the things given. So we know the mass of nitrogen gas, we know the temperature, converting it to kelvins, we know the pressure. Okay, so we need to calculate the volume of nitrogen gas. So here we go. I'm gonna go through our analyze and solve steps. So again, we need to find volume, and we have mass, so we're going to go through this little path of jumping these islands. Okay, go mass to moles island, and then moles to the volume island, okay, or volume cloud, or whatever they want to call it. Okay, so to get to the volume, we're going to start with mass. Okay, so that's the mass of nitrogen, and then we're going to use the R value next. So again, oh no, we're not going to use the R value. We're going to eventually get to the R value. We need to use the molar mass to get to moles first. So we're going to use the molar mass here. So we're going to flip it. Okay, so there goes the grams. Okay, so now we're going to use the R value. So see how moles is already at the bottom. And we need volume, which is liters, is already at the top. So we know this will need to stack like this. Okay, so we have moles, and that's good. Okay, so now we are going to get rid of kilopascals. We're going to get rid of kelvins. Okay, so we're going to go through here, and we're going to divide the pressure here, 96.4 kilopascals. Right, that'll get rid of the pressure unit, and then we need to get rid of the kelvins. So the temperature, I'll stack the temperature up here. Okay, so those are gone, and then that leaves me liters. So now you know you got all the values that you need, okay? All right, so we're going to go 32.4 times 8.31 times 298.15, okay, and divided by the 2802 and the 96.4 at the bottom, and we get 29.719 and liters, okay? And then if we round it up 2 digits, 30 liters here. Okay, and then make a therefore statement. Therefore, the volume of nitrogen is 30 liters. Okay, unit analysis is done.